So far we've done a lot of defining in this unit. There's been terms like voltage and E field, and so we're still working through how to process what will happen to a charge and how to describe its motion and describe some energy transfer. Something that I want to address with voltage is that it is a scalar, not a vector, meaning that multiple voltages can be added up, can be added together. You only need to consider the signs of your charges, so positive and negative will still play into effect. Now, like UG, like the gravitational potential energy, so when I was thinking about a roller coaster earlier in this unit that was rolling down from a hill to the bottom of a hill, I didn't really care to get an actual absolute value for height, like how far this roller coaster was above the Earth's core. I just said, look, this is h equals 0, and this is some distance above h equals 0. That's what I care about. And similarly with voltage, we don't care about an absolute value for voltage. Absolute value for voltage, no, we don't care about it. It's a reference level that we care about. Reference level is what we care about. So if I were to give you some voltages here, say this would be a 0 volt, this is a 5 volt line, a 10 volt line, and a 15 volt line. And I'll give a separate video on what equipotential voltage means. But just for right now, you could consider that there's this charge and it moves from this point in space to that point in space. And it doesn't necessarily matter the overall voltage of this space and that space. What matters is the change in the voltage. There's a reference level that we define, and we said this is voltage 0. So this proton moves across 10 volts. Starts at 10 volts, goes to 0, and we could figure out maybe the change in potential energy. Change in potential energy. We could look at, say, a lull diagram to do this. Remember that voltage is the potential energy per charge that's given. The charge here is a proton, so that's positive E, a constant that's given on your equation sheet. And I could write something like this. Well, in my lull diagram, let's say the system is my proton and my E field, whatever is causing that E field that causes the potential lines that we see. So in this side, I have no K, no kinetic energy. I have all potential energy because I start off with, what is it? This UE must be Q times V. And I start off with E, because that's my charge, positive E, times 10 volts. So I have some UE, potential due to electric field, and all of that gets converted because when I get over here, now I have 0 UE because I set my reference level to this is 0 volts. So no more potential energy due to electric charge. Instead, all of it is in K. So now I could set up this expression. Another way of examining this algebraically is I could say these are both changing. So a change in voltage is equal to a change in potential energy all over charge. Right, so my change in potential energy due to the electric field must be the charge times the change in voltage, which this is positive E. The change in voltage is 10 volts. Oh, but that is negative because you start at 10 and go to 0, so the change is negative 10 volts, and that's my potential energy change. So this makes sense because I have now lost 10 E volts of energy. 10 E volts while proton moves. So the proton moves, it loses potential energy, and it transfers into kinetic energy. Just like our roller coaster that starts up here and rolls down the hill, starts with some UE, transfers to K, and I can set my reference levels to be helpful to my problem solving. Okay, I'll see you soon.